Hello everybody, myself Jyoti and this is a lecture on Zeeman effect. Why Faraday could not observe any effect of magnetic field on spectral lines? Actually, Faraday was the first person to study spectrum of an element in the presence of a magnetic field. He placed a sodium flame in a very strong magnetic field and he should have observed Zeeman lines. But unfortunately, he could not observe any effect because the spectrometer which he was using was not having high resolving power. And that is how Zeeman effect was not like splitting of spectral lines in the presence of magnetic field was not observed by Faraday, but Zeeman observed that effect. Now, what is Zeeman effect? Zeeman was the first to observe the splitting of a spectral line in a magnetic field in 1896. So, obviously, Faraday was not able to observe, but Zeeman was able to observe. The reason being this spectrometer, the spectrometer which was used by Zeeman was having higher resolving power, and Zeeman used strong magnetic field and showed that when we place the atom in the presence of a strong magnetic field, a spectral line split up into three components in the presence of a strong magnetic field when we view perpendicular to the field. This phenomenon of splitting came to be known as Zeeman effect. Now, what were the experimental observations of Zeeman's experiment? Zeeman effect deals with splitting up of spectral lines in a magnetic field. So, Zeeman, when we are talking about the magnetic field over here, we are just saying that strong magnetic field. Kitna strong? So, strong is 30,000 Gauss or more. So, the magnetic field which we will be applying in case of a Zeeman effect, that should be 30,000 Gauss or more than that. And the field was produced using electromagnets. The spectral lines were viewed perpendicular to the field and parallel to the field. When you view perpendicular to the field, you can see three components. When you view parallel to the field, you can see only two components. Now, to observe light parallel to the field, a small hole was drilled along the axis of the pole pieces of the magnet, and the light which will pass through that small hole, it was sent through a spectrometer. The attention was focused on a sharp, intense spectral line. Now, when no magnetic field was applied, its position was a frequency nu zero in a calibrated spectrometer. And when you apply magnetic field along with nu zero, you get other two components, nu one and nu two. So, first observation, let us assume that we are viewing perpendicular to the field. So, when the magnetic field was turned on and light observed perpendicular to the field, the line under consideration, that is nu zero, splits up into three equidistant components. One component at nu zero only, and the other components equally displaced from nu zero on each side. So, nu one will be on left side and nu2 will be on the right side, that way, and they are symmetric. So if we write the frequencies of these three components, nu1, nu0 and nu2, we can say that difference between nu0 and nu1, it is equals to difference between nu2 and nu0, because nu1 and nu2, they are symmetrical, they are at a equidistant from nu0. So each of these shifts equal to delta nu equals to EB upon 4 pi m. That is difference between nu 0 and nu 1, and difference between nu 2 and nu 0, it is equals to EB upon 4 pi m. Also, it was observed that even though the light before entering the field was unpolarized, whatever light we are passing, that is unpolarized, all three components which we get, they are linearly polarized. So in perpendicular field, when we view perpendicular to the field, what you have to remember is we get three components, and these three components are linearly polarized. Nu1 and nu2 polarized at right angles to the undisplaced component nu0. So this is the arrangement. You can see we have an electromagnet, and here we have drilled a hole so that we can view parallel to the field as well. You can see the shift. This is nu0, nu1, nu2. We are getting three components, and the distance between these two components, nu0 and nu1, nu0 and nu2, it is EB upon 4 pi m. Okay. And here when we view parallel to the field, here the hole is drilled, sorry, here the hole is drilled, you can see, so that we can view parallel to the field. When we view parallel to the field, we are not getting this nu zero component, so that's why in parallel view we get only two components, and this two components, they are circularly polarized. So second observation, what happens when we view parallel to the field? So when observed parallel to the field, only two components of frequencies equal to nu1 and nu2 are observed, but nu0 we cannot observe, and separation between two components will be now 2 times delta nu, because in between nu0 nahi hai, so nu1 nu2, so 2 delta nu, so it will become eb upon 4 pi m. 2 into eb upon 4 pi m, or you can say eb upon 2 pi m. So these two components were circularly polarized in opposite directions, that you can see over here. These two components are circularly polarized opposite to each other. So normal triplet, let us define what is normal triplet. So splitting up of a spectral line into 3 equidistant components in the presence of an external magnetic field with separation between successive lines equals to eb upon 4 pi m, that is called as normal Zeeman effect, and the 3 lines are called as normal triplet. So what are the 2 important conditions? That separation between 2 lines, it should be eb upon 4 pi m, successive lines, it should be eb upon 4 pi m, and we should get 3 equidistant components. Now what happens at times, what happens that this triplet, we get a triplet, but the spacing, it is not equals to eb upon 4 pi m, it is different. In that case, that triplet, it is called as non-normal triplet. Now let us talk about anomalous Zeeman effect. Sometimes what happens is spectral lines split up into many more unevenly spaced components. Sometimes a triplet was obtained, but the splitting was not equals to eb upon 4 pi m. So this effect we call as an anomalous Zeeman effect. Now here what happens in case, whenever we talk about normal Zeeman effect, the field which we apply, it is strong magnetic field. When we talk about anomalous Zeeman effect, it takes place in the presence of a weak magnetic field. So the splitting which we get, it is different in the presence of a strong magnetic field and in the presence of a weak magnetic field. So in case of a weak magnetic field, we get complex pattern, and such complex patterns come under anomalous Zeeman effect. And to be more precise, anomalous Zeeman effect is splitting of a spectral line into either more than 3 components or non-normal triplet. Non-normal triplet in the sense spacing is not equals to eb upon 4 pi m. That is what is called as anomalous Zeeman effect. Now when we talk about strong magnetic field in the sense, one thing is like, yes, the field strength, it is more than 30,000. Second thing, it is like that the field is strong in a sense that it is able to break internal couplings. Internal couplings yani spin coupling, orbit coupling, spin orbit coupling. So when the field is strong enough to break internal couplings, it may be spin orbit or spin orbit, that is called as strong magnetic field. When we talk about weak magnetic field is such that when it is not able to break the internal couplings. Now which elements exhibit normal Zeeman effect and which anomalous Zeeman effect? So normal Zeeman effect, the one important condition is it is observed in atoms which have total spin 0. So when we say that for these atoms total spin is 0, then total angular momentum J, it will be entirely because of its orbital motion or orbital angular momentum. So J is equals to L. For the atoms which have J equals to L, for such atoms they exhibit normal Zeeman effect. For example, calcium, copper, helium, magnesium, they exhibit normal Zeeman effect. Anomalous Zeeman effect is exhibited by atoms of alkali elements like sodium, potassium, chromium, etc., and any other atoms having non-zero spin. So this is important difference between normal Zeeman effect and anomalous Zeeman effect. That normal Zeeman effect, it is observed for elements with total spin 0. Anomalous Zeeman effect, it is observed for elements with non-zero spin. You can remember the examples, and also remember third difference, that normal Zeeman effect takes place in case of strong magnetic field and anomalous Zeeman effect takes place in case of weak magnetic field. So that is about Zeeman effect, normal Zeeman effect and anomalous Zeeman effect. Thank you so much.